let's talk about limits at infinity. There's basically two different types. When your domain is going off to infinity, getting arbitrarily large, or when your range is going off to infinity, getting arbitrarily large. So let's start with the range first, and let's work with an example. The prototypical or classical examples of this are 1 over x to the n, where n is a natural number. Let's pick 1 over x cubed, and let's shift it to the right a couple units. And schematically, this graph looks, I don't know, something like this. It's going to have a vertical asymptote at the point x equals 2, where the denominator is 0. And then when x is bigger than 2, we're going to be positive and getting arbitrarily large. So we're kind of looking like that. When x is less than 2, we're going to be negative. We're taking a negative number and cubing it, and we're getting very large in absolute value. So schematically, that's what that looks like. And what we're going to say, if I tried to take the limit as x goes to 2 of f of x, well, definitely this limit doesn't exist. There's no question about that. The only way the limit could exist is if the y values here were approaching a single number. They're definitely not. But I want to have a language to capture the fact that we're escaping to positive infinity here and escaping to negative infinity there. So the way I'll do that, say we were taking the limit from the right, so that we're only considering those values bigger than 2. And so what happens, we're escaping to positive infinity. We're going to say that this limit is equal to infinity. And don't be too put off by the notation. It doesn't mean that the limit exists. It means the limit doesn't exist, but we know something about the way that it doesn't exist. In fact, what this is supposed to mean is that as those x values get closer and closer to a from the right, in this case closer and closer to 2, then your y values are growing without any bound at all. So no matter what number you pick, no matter how big it is, the y values are going to be even bigger than that no matter what. We call that an infinite limit. And you could also say, what if you wanted to take the limit from the left? And by the same analogy, since you're getting large in absolute value, but you're negative, we say that we're going to negative infinity. So usually infinity just means large and positive, and negative infinity means that you're growing more and more negative without any bound below. So that gives you an idea about these infinite limits when the y values, when the range of the function is getting very large or getting very large in absolute value, but negative. So the limits don't exist, but the way that they don't exist is very particular. To keep it even more simple and clean, these limits have to do with vertical asymptotes. Now there's another kind of limit we can look at, and that's going to be a limit as your x value goes to infinity. And you might expect that that has something to do with horizontal asymptotes, and that's completely true. So let me explain it. Let's take a different function. Let's take f of x equals arctan of x. So you may remember that the tangent function, the graph kind of looks like this. You isolate negative pi over 2 to pi over 2. So that graph looks like, so that has two vertical asymptotes. Arctangent being the inverse function. The way you find the graph of an inverse function, you draw that line y equals x and then flip it over. Or if you think y equals x is a mirror, then you're looking at the mirror image. And when you get the graph of arctangent, it's going to look like this. And it's going to have two horizontal asymptotes. So the vertical asymptotes for tangent become the horizontal asymptotes for arctangent, which then means that this y value for arctangent is going to be pi over 2. And this one has to be negative pi over 2. So say that I want to take the limit as x goes to infinity of arctan of x. And I have to imagine, well, so what's that going to mean? So as my x values get larger and larger and larger and larger, as my x values grow without bound, are my y values approaching a single value? And the answer is yeah. As your x values grow without bound, your y values are now approaching this horizontal asymptote. They're approaching pi over 2. And I can also say, what if I take the limit as x goes to negative infinity of something like arctangent of x? And what this means is, instead of going off to the right, I'm going to let x get more and more negative, but without bound. So x is going to be escaping to negative infinity. And what's happening to the y values? Well, in this picture, you can see those y values are going to be getting closer and closer to that other horizontal asymptote. And I didn't draw it completely to look like that, but you get the idea. And so this is going to be equal to negative pi over 2. So the way you can conceptualize it, the way you can keep it straight in your mind, is these limits equaling infinity or negative infinity. That's going to have to do with a vertical asymptote. And a limit's going to be equal to plus or minus infinity when x is going to a, and a is the location of that vertical asymptote. Now, when you're thinking about the limit as x goes to infinity or negative infinity, that has to do with horizontal asymptotes. And in that case, the limit itself is going to be the y value of the respective horizontal asymptote in many cases.